Welcome to Sunny's Mindset Lab podcast. Today, we're exploring the art of statistical thinking. This conversation is about learning how to think clearly about numbers, data, and claims in an increasingly data-driven world.
Thank you, Sunny. This book was written to help people move beyond formulas and develop intuition for understanding data and uncertainty.
That's exactly what I want to dive into. It feels like we're surrounded by data, but you often hear that you can use the same numbers to prove completely opposite points. How is that even possible?
It's not only possible, it's one of the most common ways statistics are used to mislead. A perfect example is something visual. Take a look at these two charts. They both show the exact same data on global temperature change. Wow, okay. Looking at them side by side, the one on the left looks like an absolute emergency, a really steep, scary climb. But the one on the right, it looks flat, like nothing is happening at all. So which one is telling the truth? That's the trick. They both are. The data is identical in both. The only thing that's changed is how the y-axis, the vertical axis, is scaled. Stretch it out, and even a small trend looks like a mountain. Squeeze it down, and a significant trend can be made to look like a flat line.
So it's a visual illusion, really. Why would someone do that? What's the end goal?
It's about controlling the narrative. If you want to create a sense of urgency or panic to drive action, you use the stretched out axis. If your goal is to create a sense of calm and suggest that an issue is being overblown, you use the compressed axis. It's a remarkably simple and effective way to change the emotional impact of the data without ever touching the numbers themselves.
That makes a lot of sense. So if we can't always trust our eyes when we look at a graph, a lot of us fall back on what feels like a solid, trustworthy number, the average. We see it everywhere. But I get the feeling from your work that the average might have its own set of problems.
You're exactly right. The average is often seen as this single point of truth, but it can be just as misleading as a manipulated chart. It hides as much as it reveals.
Just so we're all on the same page, when we say average, we're usually talking about the mean, right? You just add everything up and divide by how many there are.
Correct. And the mean is incredibly useful. It's a powerful tool for taking a huge, messy pile of data and summarizing it into one number that's easy to understand. It's the hero of so many news headlines and business reports for that very reason. But that simplicity, it comes at a cost.
Okay, so what is that cost? What crucial information are we losing when we just boil everything down to that single average number? What's the story that it's hiding?
It completely erases the story of variation, of the shape and distribution of the data. And that story is often the most important part.
Let's use a practical example from the book. Imagine you're a manager looking at the performance of two salespeople, A and B. You pull up the report and it shows that for the past year, both of them had average monthly sales of exactly 100 units.
Okay, so looking at this chart, they look identical. As a manager, I'd probably think, great, they're performing equally well, they're interchangeable.
Exactly. That's what the average tells you, but it's wrong. They are not interchangeable at all.
So what's the hidden story here? The hidden story is in the variability. When you look at the monthly data, salesperson A is Mr. Consistent. Every month, it's 98, 100, 102, very reliable. But salesperson B is a roller coaster. One month, they sell 200 units, maybe landing a huge client. But the next 2 months, they sell 0. Their average is the same, but their performance styles are polar opposites. And that changes everything. Salesperson A is dependable for forecasting, but salesperson B might have that superstar potential even if it comes with a lot of risk. You can't make a good management decision just from the average.
Okay, that's a powerful point about how one number can hide the truth within a single data set. So what happens when we start comparing two different sets of data? I feel like that's where things can get even more confusing. It leads us right into one of the biggest traps I've heard of, mixing up correlation and causation. Yes, this is arguably the single most important concept in all of statistical thinking. It's a trap our brains are wired to fall into. To illustrate just how absurd it can get, look at this chart. It plots year by year the number of people who drowned by falling into a swimming pool against the number of films Nicolas Cage appeared in.
No way. The lines, they track each other almost perfectly. That's uncanny.
So what are we supposed to conclude here? That we need to ask Nicolas Cage to stop making movies to save lives? Of course not. And that's the point. This is what's called a spurious correlation. It's two things that are statistically linked. They move together, but there is absolutely no real-world causal connection between. So this is the golden rule right here. Just because two things happen together, it doesn't mean one is causing the other. In a case as absurd as the Nicolas Cage one, what's really going on? The key is to always be a detective and hunt for a third hidden factor, what's often called a confounding variable. In this case, it's pretty simple: summer. The weather gets warmer, so more people go swimming, which sadly leads to more drowning accidents. And at the same time, summer is when movie studios release their big blockbusters. So summer heat is causing both things to rise. Nick Cage movies and drownings aren't causing each other.
That makes perfect sense. But you see these kinds of headlines all the time. Study finds link between X and Y. How do these strange and likely false correlations make it into the news?
Well, this comic about jelly beans explains one of the most common ways it happens. It's a practice some call p-hacking, or more simply, cherry picking. Imagine scientists test for a link between jelly beans and acne. Nothing. Then they test purple jelly beans. Nothing. Brown, pink, blue, nothing. They run 20 tests and find nothing. But on the 21st test, green jelly beans show a link, just by random chance.
And then the headline is, "Green jelly beans cause acne."
Exactly. You ignore the 20 failed experiments and only publish the one that showed a result. If you torture the data long enough, it will confess to anything.
Okay, so cherry picking in small studies can create these false correlations. But that leads me to a big modern question. What about big data? The thinking today is that if we just have a massive sample size, millions of people, billions of data points, surely that protects us from these random flukes and errors, right?
That's a very common and very dangerous assumption. Big data doesn't automatically solve these problems. In fact, sometimes it can make them worse.
Let me give you a real-world example. It's a famous landmark medical study on whether taking aspirin could prevent heart attacks. And this wasn't a small study. It was huge. It involved over 22,000 male physicians.
Okay, 22,000 people. That's a massive sample. You'd expect to get a pretty reliable answer from that.
And they did get an answer. The results came back, and the conclusion was that there was a statistically significant link between taking aspirin and having a lower risk of a heart attack.
That phrase, statistically significant, sounds so official and so important. To me, that sounds like it's case closed. A really powerful effect was found.
It sounds that way, doesn't it? It implies importance. But all statistically significant really means is that the result is unlikely to be due to random chance. It doesn't say anything about the size or importance of the effect itself.
Okay, so what was the actual effect? How much did it lower the risk? When you looked at the actual numbers, the difference in the risk of having a heart attack between the group taking aspirin and the group taking a placebo was less than 1%. It was 0.77%. Wait, that's it? Less than a 1% difference? How can something so tiny be called significant?
And that is the big data illusion. With a large enough sample size, like our 22,000 men, you can put the data under a statistical microscope. And under that microscope, even a minuscule microscopic effect can be proven to be real, meaning not just a random fluke.
So let me see if I get this. Statistical significance just confirms the effect probably exists. But practical importance asks the real-world question: is this effect big enough to actually matter to anyone, to change your behavior?
You've nailed it. And with big data, you will find thousands of statistically significant results that have absolutely no practical importance in the real world.
So a massive sample can make a tiny effect seem important. Can it also just be flat out wrong?
Absolutely. In fact, a huge sample can magnify an error if the sample itself is flawed. The most classic example is the 1936 U.S. presidential election poll by the Literary Digest. They polled over 2 million people, a staggering number.
2 million! They must have gotten it right.
They predicted a landslide victory for one candidate, and the other candidate won in a landslide. They were spectacularly wrong. The problem wasn't the size, it was who they asked. They polled people from their own subscription lists and from car and telephone registries. In 1936, during the Great Depression, that skewed the sample heavily towards wealthier Americans who had a different voting preference. Their massive sample wasn't representative of the actual voting public.
This is all fascinating, but I have to admit it's also a bit intimidating. We've seen how graphs can lie, averages can hide the truth, correlations can be meaningless, and even huge datasets can be misleading. So for the rest of us who aren't data scientists, what are we supposed to do? How can we arm ourselves against all this potential misinformation?
That's the most important question. And the good news is, you don't need a degree in statistics. You just need a healthy dose of skepticism and a simple toolkit of questions to ask.
Okay, I love that. A toolkit. A mental checklist we can run through whenever we see a news story or a study or a chart that makes a big claim. What's on that list?
It really boils down to 4 key questions. If you can get in the habit of asking these 4 questions, you'll be able to spot the vast majority of statistical manipulation out there.
Let's go through them. What's number 1? First, who was sampled? Think of that 1936 poll. Is the group being studied representative, or is there a sampling bias? Okay, number 2, what's the real-world effect size? That's our aspirin study. Is the finding just statistically significant, or is it practically important? Right. And number 3 has to be our Nick Cage question.
Exactly.
Is it correlation or causation? Look for that hidden third factor that could be driving both. And finally, I'm guessing we go back to the very beginning. We do. Number 4 is, how is the data being presented? Are the axes on the graph being stretched or shrunk to tell a particular story? Asking these 4 questions forces you to slow down and think critically.
I really like that framing. It's not about being able to run the calculations yourself.
Not at all. The goal isn't to turn everyone into a statistician. The goal is to equip people to be better informed citizens, parents, employees, and consumers. It's about developing an intuition, a feel for when a claim based on numbers feels right and when it feels a little bit off. It's about empowerment.
Thank you for such a clear and thoughtful conversation. This discussion gives our listeners a practical way to approach data and claims with more confidence.
Thank you, Sunny. I hope this conversation helps people think more critically and calmly when they encounter numbers in everyday life.
This has been Sunny's Mindset Lab. Thank you for listening, and we'll see you in the next episode.